Let's take a look at bit banging on the R32V2020 RISC CPU. The target FPGA card we're using has a bunch of I/O pins, so let's hook up a scope to those pins and see what we can do with bit banging. Here's a first cut at the code. The line 8 loads the peripheral address register with the register of a port which we built. Store peripheral long SPL R0 will write out a 0 to the port, and then SPL1 will write out, R1 will write out a 1 to the port, and then we branch forever. The VHDL code consists of an 8-bit register. We have another example above that of the register used for the LEDs, so it's the same thing with an entity, new entity, and those go out to the I/O pins through the top module. The result is a square wave with a frequency of 2.7 megahertz, and note that it's asymmetric, and we can take a look at why in the original code. The CPU is unoptimized, and it takes 6 of the 50 megahertz clocks on the FPGA to execute an instruction. So at 20 nanoseconds a clock, 6 clocks is 120 nanoseconds per instruction. This could probably be optimized down quite a bit, and there's no pipelining really here. It's just one stage after another, and when all stages are complete, the next stage starts to execute. So looking at the code, that's the SPL R0 takes one set of 6 clocks, or 6 times 20, 120 nanoseconds, and the second one takes another 120 nanoseconds, and the branch also takes that same amount of time. So if we want to make it symmetric, all we really need to do is add a no-op between the first store and the second one, and that will make the waveform symmetric. Let's take a look at that. Here's the source code with the no-op added between the SPL R0 and the SPL R1. Let's take a look at the scope and see what it did. And as expected, it made the result a symmetric result with a time of about 480 nanoseconds, or 4 of the instruction times of 120 nanoseconds. That gives us a bit banging frequency, if we want symmetry, of 2 megahertz, which is a pretty decent bit banging rate, really. Certainly better than you can get from an Arduino or some other 8-bit processor, which itself is only running at in the case of a 6502, maybe only running at a megahertz. It definitely can't bang out bits that quick. So pretty nice result, pretty decent performance for something that's really completely unoptimized at this point. Of course, sending out just the square wave from a part and consuming the whole processor resource to do it is not a very good use of resources on the part, but it does demonstrate the raw speed. What would it look like to do something a little more complicated, like write out a test pattern, an 8-bit test pattern out that same port? Well, it's really not a lot of code change here. We're basically going to use R8. Instead of having the R0 and R1, we're going to use R8 to hold the test pattern. In this case, we're going to do 5A because it's alternating ones for the first 4 bits and then alternating the other bits for the next 4 bits. And we'll make a bit count and load that in R9. To send that out, all we have to do is the same SPL of R8, and then we use the instruction shift right, and then we add -1 to R9 and branch if that add produced the result that was not 0. Here's the shift right by 1 instruction on the programmer's card for the R32V2020, and it takes a source and destination register, so you could shift value from one register to the other, but in our case we're going to leave it in the same register. And here's the branch not 0. As you can see, it operates on the ALU. I've got the branches probably not set up the most efficient way they could be. Some branches work off ALU results and some branches work off compare results. So you have to bear in mind, if you're using the branches, which type of operation you've done. If you want to use the compare, the immediate instruction prior had to have been a compare instruction. It could actually be farther back in the stream, but an ALU instruction would overwrite these bits and vice versa. So branch not 0 will go to a relative address, and we really need to add a branch at the end here to the endpoint, otherwise it'll just keep running and there's no code. It's probably set to 0, but the program counter will keep going up all the way, and 0 is a no-op in this machine, so it won't do anything immediately bad, but it will probably wrap in the data space, and who knows what will happen. I haven't really played with it that much, but properly it should have the equivalent of a while 1 in C here, a branch to self. And here's the result. The bit stream is written out 0 1 0 1 1 0 1 0. Of course, it's hard to tell the ends that are there, but it's working. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindie where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.